Hello everyone, welcome to the FIFA Fever. You must be asking why today Newton's third law. And let me ask you the question then. Why 90% of the students fail to understand Newton's third law? That's the biggest question. And today I'll break the biggest misconception about the Newton's third law and help you understand it in a more simplified manner. And that is the objective of the class. So let's move forward and attack. And welcome to the physics of the kick today. Now, have a look on the scene. So if you look carefully, you can see that the foot is applying a force on the ball. Now, can you tell me what is happening to the foot? Is there any force is applied by the ball on the foot? You must be saying yes. And you are very much aware that if the foot is applying force on the football, so the football is also applying a force on the foot. And you call it as a action reaction pair. Am I right? Yes. Okay. Now this millisecond actually breaks our intuition. What basically one thinks, if I ask you what you think, that which comes first, the action or reaction, definitely you will say, sir, action came first and then there is reaction. So you think that action is the cause and reaction is the effect. So what is according to you is that when foot applies force on the football, then after some time the football applies force on the foot. And here, the more than 90% of students fundamentally misunderstand physics of this exact millisecond. What is happening in this exact millisecond? That's the key idea. Okay, so let's move further and understand. So, this is the fatal flaw of cause and effect. And nothing to worry, it's not your fault because this misconception of cause and effect, it arises from the definition. Let me just show you with the example. Let's say at t equals to 0, the boot strikes the ball. At t equals to 1 second, the ball compresses, and after that, after some time, the ball pushes boot back. That is exactly what we think or what you think after reading it one or two times without understanding the Newton's third law in detail. And that there you make the mistake. Action comes first, then reaction is there, and this falsely implies a sequence. And we tend to believe that okay, if there is action, there is equal and opposite reaction. Action comes first, reaction comes thereafter. This is what Newton did not intend to. There is no cause, no effect. Both happen simultaneously. So both the forces are born together. The moment the foot pushes the football, the exact moment the football pushes the foot with exactly same force. Neither comes first, neither cause the other. They act at exact same frame, same time, simultaneously. That's the thing. That's the kick. So I hope the very first misconception is resolved here. So what is that? Action is not the cause, reaction is not the effect. Both act simultaneously. Why this error most of the students make? The thing is with the old vocabulary. What happens that if you look carefully, because of the old vocabulary, we call it action reaction, and in layman term or you can say common man terms, what we think that whenever there is action, then there comes the reaction. But when it comes to Newton's third law, this is not the real sense of action reaction. So what I would suggest, you must call it interaction pair rather than action reaction pair. So let's erase the old vocabulary and have a good definition of Newton's third law in order to avoid any kind of confusion, misconception in the near future. So action and reaction are only naming conventions that confuse the timeline. If object A exerts force on object B, then object B exerts a force on equal magnitude and opposite direction on object A. And better to call it as interaction pair. So force of foot on the ball and then force of ball on the foot. See, the two forces, they always act on different objects. Therefore, they never cancel out. Action and reaction forces act on entirely different object, and you must remember it because they belong to different bodies. So whenever you draw a free body diagram, let's say I'm drawing a free body diagram of football. This is a football, and let's say gravity is acting downward. Let's say the mass of the football is m, and g is the weight, acceleration due to gravity. So mg is the weight acting downward, and let's say some force F is applied by this boot, okay, on this football. So definitely this football and mg are acting on the same object, the football. Since they are not action reaction pair, they are not interaction pair. But if the foot applies a force F on the football, definitely this ball also applies a force F on the foot in opposite direction. And this is the action reaction pair. If you understand carefully, this is the action reaction pair. This is the action reaction pair. They are acting on different object. So whenever you draw a free body diagram, be careful while drawing it. Okay. Be sure that action reaction pair should not be on the same object because they act on the different objects. So like I mentioned, if the gravity is acting downward, force by foot is acting in this direction. So the same object trap. Force acting on the same object are not interaction pair. Clearly, I have mentioned you earlier also. Here you can also see, be careful. On a single object, you cannot draw action reaction pair. I'm telling you a simple story. Okay. Once I called one of my students, I asked him that block is placed on the top of a table. Draw me action reaction pair. So what is the first thing he did? He took the block, made its free body diagram. He said, sir, this weight mg is acting downward and the normal reaction is acting upward. So mg is the action, normal is the reaction. That's not, that's completely incorrect. Action and reaction pair cannot occur on the same object. Interaction pair are not on the same object. You can see here, gravity pushes the ball downward, foot pushes the ball forward. Both act on the football. Therefore, they are independent forces and not a Newtonian pair. So keep this in mind. The third thing that you have to keep in mind, the nature of the force remains identical. The true interaction pair will never mix force type. It means that if A is applying a gravitational force on B, then B also applies gravitational force on A. For a magnetic force, there will be a magnetic force. For a gravitational force, there will be a gravitational force. For a friction, there will be a friction. So do not mix the fundamental nature of the forces. What I mean to say that these forces, action and reaction pair, or you can say interaction pair, they are always of same nature. Their nature should not be different. If A is applying a force of electromagnetic nature on B, then B must also apply a force of electromagnetic nature on A. What I have told you, that action and reaction pair, they are bound together, simultaneous interaction is there, they have equal magnitude, have same vector length, they apply force on opposite directions, they act on different objects, and they are of same nature. So this is the key conclusion that one must learn from this example of FIFA football. I hope you must be loving it. So the diagnostic matrix, if I say true pair, you can see here objects acted upon different object, it should not be same. Action reaction pair should act on different object. Nature of force should be identical, it should not be mixed. Directions, that exactly opposite. If you just see the directions, they are exactly opposite. Direction should not be the same. Timings simultaneously. This is the biggest flaw, biggest misconception which the student make. No. So you can see here the hand is holding the ball, applying the force. So ball is also applying the force on the hand simultaneously. The head is kicking the football, so the ball is also applying the force on the forehead simultaneously. Contact force is there between the post and the ball. So the ball is also applying a contact force on the post altogether. Similarly, when you are pushing the ground backward, the ground is pushing you forward simultaneously, and that's help you to walk. Is Newton's third law always true? I'm asking you. So for everyday mechanics on a football pitch, the law works perfectly fine. But at the extreme of the universe, there is a hidden limitation. One must understand. Now, what is the limitation? Let's try to understand with the help of example. So let's say we have an object A and an object B at a distance of 1 light year. Now, here is the trap. So object A, let's say, has some mass ma and object B has some mass mb. So if someone asks you, what is the force right now applied by object A on B? So you will say that force on B applied by A, and this is the force on A applied by B. So what is the force on B applied by A? Let's just talk about the magnitude. You will say G mass of A into mass of B by R square, where R is the distance between the two. Now look this formula carefully. If you are very much aware with the gravitation, you must be knowing that this is the gravitational field intensity, E. So it is not the object A which applies force on B, but it is the field intensity of A, which is G ma by R square, which applies force on B. So simply you can say that force on B is equal to field intensity at any point of A multiplied by the mass of the B. So in order to calculate the what is the force on B, I can simply take the help that I just need to calculate the field intensity of A at any point, and then I simply multiply the B placing over there. So I can come to know that what is the gravitational force acting between B and A. So similarly, force on A by B will also be G mb by R square. So what is this? This is the field intensity at any point by B, let's say at a distance R. And if you multiply it by the mass of A, you will get the force, okay, by B on A. Now here is the twist. Let's say that we move the ball B by some distance D. And let's say the new distance between A and B is R prime. Now what do you think what will happen? In this case, Newton's third law looks good, valid. And it is true. The same force is there, G ma mb by R square, G mb mb by R square. What's the scenario here? So what is the twist here? See, the field intensity E much moves like light. So it travels with the speed of light. So any message of field intensity, I'm telling you, listen this thing very carefully. Any message of this intensity, travel message of field intensity travels with the speed of 3 into 10 to the power 8 meter per second. That's the speed of message. So if B changes its position from this point to this point, changing its distance from R to R prime, do you know what will happen? As A has not changed its position, so at any particular point, its field intensity has also not changed. So if the field intensity at this point by A is, let's say, Gma by R square, so field intensity at this point by A will be Gma by R prime square. And since distance is changed, so field intensity of A is changed. And since field intensity is changed, so you can see that the force on B will be this one now. So this was the earlier force, and this is the new force. B has changed its position. So accordingly, the field intensity at this point must also change. But the message that the field intensity has changed will be received by A much later. Ah, that's the twist here. So the A will come to know about the change field intensity of B at this point after a certain period of time. So even though B has changed its position from this to this point, the field intensity by B still here will be G mb by r square, even though B had changed its position. Means the A will come to know about the changed position of B only after a certain period of time, and this period of time will be decided by the speed of the masses. You can say like this, that the intensity is more like a massage and it will transfer only with the speed of light. So definitely it will take some time to cover distance which is much larger in this example, that is close to 1 light year. So imagine two objects spaced exactly 1 light year apart pulling on each other. Suddenly object B moves. Does object A feel the change immediately? No. That's the answer. A will not feel the change immediately. And at this point, one can say that the B has changed its position. The force on A is the same like the previous one, but the force on B by the A is changed. It's all about speed. As I mentioned earlier, the change in the previous slide, the change in gravity cannot travel instantly. Information propagates at the speed of light. So obviously, the object A still experiences the old gravitational field by the B, not the new one, until the golden ripple of information physically reaches it. So this is the golden ripple, and this information of the changed field intensity of B will take some time to reach to the A, and therefore to experience the new force by B on A, it will take some time. You must be thinking, okay, no, the Newton's third law is not always true, but check here. Newton was not wrong. Yes, he was not wrong. His law is an excellent approximation for classical mechanics. So when up to classical mechanics, it's perfectly fine. But modern relativity reveals that momentum isn't just carried by matter. See, up to classical mechanics, what we think that momentum is carried away by matters. But when it comes to the modern relativity, modern physics, what we know that it is not just the matter which is carrying the momentum, but also it is stored in the fields. So what happened when B changes its position, the field stores the momentums. So the true unbreakable rule of universe is the conservation of momentum. So momentum conservation will remain true here. So did the foot kick the football or did the football kick the foot? You know, you know the answer. So if you know, you know. Both happened at exactly the same instant. So I hope you enjoyed the class a lot. There was a lot of explanation in detail, especially when it comes to the relativity, when it comes to the distance up to light year, what happens to the Newton's third law over there. So what happens that most of the time you do not come across such examples. Physics cannot be learned by just simply rote memorization. Live it, feel it, understand it.